We'll work one problem on rigid plane frame by stiffness method. Last problem. So the same problem we have already worked by stiffness method. The same problem we work by this flexibility method also and verify the results. So consider a frame A, B, C, D subjected to a concentrated load of 90 kilonewtons at 2 meters from the end C, and the length of D is 6 meters, length of DB is 6 meters, this we will take 3 meters. So this 2EI, 2EI, and here it is EI. Here this sway of 20 kilonewtons. This is the problem we have worked by stiffness method. Same now we will work by flexibility method also. We will follow the same step. First step, degree of indeterminacy, because it is a rigid plane frame, because all joints are rigid and all are one-dimensional member. So that's why it's frame structure, rigid joint, so it is called rigid plane frame. And all members lay in one plane, that's why plane frame. Rigid plane frame structure. And it is unequal leg, and also it is orthogonal, it is called, because all legs are vertical, not inclined. So the degree of indeterminacy for such structures, it is given by 3m plus or minus 3j minus any imposed external condition. This is the formula we have for finding degree of total indeterminacy of rigid plane frame. Here, of course, imposed external condition, that it is nil here. No condition has been imposed in the form of external hinge or external condition, nothing has been imposed. So this is 0. And here m is number of members, and that is equal to 1, 2, 3. R is number of support reactions, 3 here, 3 here, it is 6. And J is number of joints, A, B, C, D, that is 4. Therefore, total degree of indeterminacy is 3 into 3 plus 6, that is 9 plus 6, 15. 15 is the total number of unknowns, and equations of equilibrium per joint is 3, J is 4. So 3 into 4, 12 equations are available for solving 15 unknowns. So 15 minus 12, that is 3. So 3 unknown forces cannot be solved by the equations of equilibrium available. This is defined as the total indeterminacy of forces. And external indeterminacy is R minus 3, that is 6 minus 3, that is 3. So this given frame is externally indeterminate to the degree 3, and internally it is determinate, because the external total indeterminacy is also 3, external indeterminacy is also 3, therefore internal indeterminacy is 0. Already I told, all single story rigid plane frames, you can take it as, just like beams, you can take it as externally indeterminate structure. So only external reactions you have to choose as the redundant force. Here, now since 3 is the degree of external indeterminacy, 3 of the external reactions out of 6 can be chosen as the redundant. For those 3 reactions you can choose, there are 2 ways here. One way is you can remove either support D totally, thereby you are removing 3 reactions here, and structure becomes a cantilever type of frame, so it is determinate. Or you can remove support A and make the structure determinate. Or you can make this hinge and this roller. That is another way. Either you can remove support C or D, or you can make support A hinge and this roller, thereby you can make the structure determinate. Or you can make this hinge, and you can impose one external condition in the form of hinge here, either as B or C, you can make the structure determinate. While introducing that releases, make sure that structure is stable. Don't introduce two internal hinges here. Now here we will make the structure determinate by removing the support D. That means three reactions I have removed. So I'll make the support D removed and the redundant directions, coordinates are 1, 2 and 3. So this is the basic determinate structure with determinate structure with redundant coordinates. So 1, 2, 3 are the redundant coordinate directions. That is, this is HD direction, this is vertical reaction VD direction, this is support moment. The three reactions we have removed and their positive directions we have selected in the direction of these coordinates. So this is the first step. That means the redundant force we can represent it in the matrix notation. R is equal to this VD, HD, VD and MD. Because HD is 1, VD is 2, 3. This is 1, 2, 3. It is 3 by 1 matrix. This is redundant vector we have chosen for this particular structure. And since you have removed this support D on account of this particular loading, as I told you earlier, in the beginning in the original structure there is no displacement. Now since we have removed three displacements will occur here. That's horizontally it moves, vertically also it moves, and then the rotation also. So displacement will be there on account of the loading, so that dl is nothing but this dl1, dl2, dl3. This is on account of the external loading along 1, 2, 3. I will be getting displacement, horizontal displacement, vertical displacement and rotation, because this has been removed. So there is going to get this displacement. And dr, that is external imposed displacement along these three coordinates, nothing is given in the problem in the way of support settlement or support rotation, nothing is given. So that is also 0 here along the three coordinates. Therefore, the displacement vector, we can take it as dl dr minus dl. That is nothing but minus dl1 minus dl2 minus dl3. This we have to determine, because since we have removed that support along this direction, displacement occurred due to the given load, we have to determine this displacement that will be corresponds to D. R is there, then we can use our force displacement relationship. R is equal to F, or D is equal to Fr. So we have force displacement relationship, force displacement relationship in terms of flexibility. B is equal to F into R. So D you have to find out. Yes, also we have to generate. It is the property of the structure, and R is the redundant. Therefore, R we can determine as F inverse D. So this is your first step. Now, what all the unknowns which we have there, that we have to estimate during our next subsequent step, second and third step. Second step, we have to determine this D. Third step, we have to generate flexibility matrix. Then finally, last step, we can generate this R. That's all the actual problem. Then second step, we will take to find D. To find D, that is displacement vector. That already I have told it is due to the load. This already you know that notation. So you take that basic determinate structure. This is the basic determinate structure A, B, C, D, and the given external loads are, this is 90 kilonewtons, this is 20 kilonewtons, and this is 2 meters, this is 4 meters, 6 meters, and 3 meters. Now we have to estimate all these DL1, DL2, DL3. So we have here DL1 in this direction, DL2 in this direction, DL3 in this direction. That we have to estimate on account of this loading. Right? So this we will work out by adopting dummy load method. So that you can say, let us use dummy load or unit load method for finding the displacement. According to that unit load displacement, this DL1 is given by sigma of integral mm1 dx divided by EI. That's the formula we have as per this dummy load method, where m is the bending moment at any section in the members of the given structure, and small m1 is the again bending moment at those corresponding sections due to unit load being applied in the direction of that DL1. So that if you have to evaluate and find out that integration limit also, because at any section bending moment varies depending upon the loading. In this particular structure, in portion CD, there is no load at all. So we have to take a section. Similarly, the portion CE here, there is no load. If you go from right to left, if you move, here no load on the column. In the field, in this portion, there is no load. Then whereas in this portion, this 90 kilonewton will be acting, that will be active from E to B. So I need another section. Then again, after B to A, there is no load, one section is enough. So like that, we have to select 4 different sections and find out the bending moment due to the given loading first along those sections, moving from right to left, and again after that evaluate this M for all these sections, so that entire structure is covered, that is CD portion, CE portion, EB and BA. These sections we are selecting wherein the loading variation is not there, starting from one end of the structure. So next we have to apply unit load, and at the same section we have to evaluate the moment. Then both after knowing M and M1, we have to integrate between the limits from 0 to this height 3 meters, then 0 again here 0 to this length, 0 to this length, like that we have to apply, and those limits we have to integrate it and add all those things, so that for the total structure we get the displacement in the direction of DL1. Similarly, DL2 is equal to sigma of M m2 dx by di. This m remains same, capital M. M2, we have to apply unit load along L2 or two direction, and we have to evaluate. Like that dl3 is also given by sigma of mn3 dx by di. These are the formula we have for evaluating these displacements dl1, dl2, dl3, or in other words, to compute this is the actual methodology we are following. So the values of capital M, small m1, m2, and m3, you can prepare a table and you can get the values in that fashion. M1, M2, M3 are tabulated as below. So these sections also is indicated. First section, as I told you, I have to take the section x1 there, and I have to measure the distance from end to D. This covers CD portion, because moment about this section, by taking towards right side, it is same from point B to point C. Next, here also, because the orientation change, this is beam. Here also we need to take another section and at a distance x from end C. Then from C to E, whatever moment we have taken at x2, it is same. The moment it crosses E, this 90 kilonewton will be active. So the moment will be different. I have to take another section x3. It is from this side. From E I have taken, from E to B. Next, another section we need, because here this 20 kilonewton sum will come into picture, and moreover it's a column member, so member also change. So another section I need, and distance I will measure again from B. This is always better to take in this fashion. Or you can take from right to this point, again from left side also. You can do it either way, whichever is convenient, you can adopt. So I will just prepare a table. So segment, I will write segment. There are 4 segments. One is DC, another CE. Next, I have EB. Next, I have BA. So these 4 segments I have. Then origin for measuring the distance. For DC portion, I will take D as the origin, because X I am measuring from DN. For C portion, X I will measure from CN, C or D, both are same. And for EB, I will measure the distance from E, and for BA, I will measure the distance from B. And the limit, so the total length, variation of length, it is for DC portion, x is equal to 0 to x equals 3 meters. That is 0 to 3. Then for CE, it is again x equals 0 to x equals 2. Then for EB, it is x equals 0 to x equals 4 meters, because E is the origin I have taken. And for BA portion, it is again 0 to 6, x equals 0 to x equals 6. Then EI value, that's also changed. You take it. For DC portion, it is EI. For CE, it is 2EI. This is 2EI. This is also 2EI. They are the EI values. If it is EI is constant, then you can just discard that particular column. Then M, bending moment due to given load. I told you M we have to calculate. So I will consider the free body diagram towards right side. Here for X1, this portion, that is for DC portion. So there is no load. naturally the moment is 0. Again for x2, there is no load, this again m is 0. Then here, so there is only 90 kilonewton load and it is there from, it gives a moment equal to 90 into x, it gives in the anti-clockwise direction, resisting will be opposite to that, so it gives a hogging type of moment, so it is negative. So it is minus 90 into x. But when taking the free body diagram, we are taking towards right side only, full, this also we have to take it fully from here to here. That is 90 into x plus 2 I will take it, so that x, when it is 0, it will be 0, x minus 2 I have to take, so that when x is equal to 2, this moment will be 0. That we have to carefully select it. This is minus 90 into, of course here there is no load, straight away I will take 90 into x. I can take it straight away. Or if I measure the distance from here, then I have to take x minus 2. So if at all you have loads here also, I think it is better to take distance from C or whichever is convenient. Shall we already have taken x here? We will measure it
because
from there.
We treated it as a separate span.
That is no problem at all. Then, or distance I have to measure it from here, as I told you. Once I have to take from right to left and left to right. It may create some problem in determining horizontal loads. Otherwise, as long as loads are all vertical, you need not have to bother. Straight away we take minus 90 minus x, and here, when you come here, again, moment about this, it is equal to 90 into this distance. It is 4 meters, it is 360. And this also will give a moment 20 into x. Both are anti-clockwise, so that is minus 90x. This is clockwise, this also clockwise, not anti-clockwise. Clockwise negative minus 90x minus 360. So here clockwise becomes negative because it gives hogging moment. Because in the front moment, if it is clockwise right side, it is giving hogging type of moment. That's why we take it as negative. Don't be under the impression always clockwise positive. It is not the thing. That here hogging and sagging, we have to take it as section. Then M1, M1, M2, M3, we have to work out. That completes the table. So major portion of the work is this table. So how to prepare M1? I told you we have to apply a unit load in the direction of that coordinate 1 unit we have to apply. It's the same sections, x1, x2, this is E, this is C, this is D, B, D. Here it is x3, here it is x4. So here moment M1 is as usual, it gives a moment in this direction, that is anti-clockwise. So here it is clockwise, so but it gives a sagging type of moment, positive. So it is 1 into x for the portion DC, x1. And similarly for x2, it is 1 into this distance. It is again same sign convention, that's 1 into this total height.
3.
Because at all these points, it is same lever arm, that is 3 meters. So 1 into 3, that is 3. Next, here also, it is 1 into 3. It remains same. Here you have to be careful in this portion, because direction is reversed. We are moving up, then on the beam, then on the column we are coming. Since again, same column we are moving in the downward direction. So this load, I have to consider here acting like this and like this. If I take value will not alter. at this particular point B, I will consider the same load, one like this, acting one in this direction. Value will not alter at this point B. This one, value will not alter. Now in this case, this load and this load, that one, it will give a couple. That is nothing but 1 into 3. So that anyway, it is there, that 3. In addition to that, this 1 into x, we have to take. So this point, you have to be very, very careful. Because this column is over, this beam is over. When we come again to the column, this particular portion, we are ignoring. In most of the cases, we will end up with erroneous result. This is the confusion which will create in this strain energy method. That you should not do. Because here it is okay. It is only column, same member, column member. This is beam, absolutely no problem. Beam is a horizontal member at the same distance. But here it is again a column. We are moving in the opposite direction of the first column. So we have to replace that load by another equivalent load. If I have studied in applied mechanics in first semester or second semester, any load, you can consider it to act at another load by similar type of one direct load and a moment. That principle we have to adopt. That's called Saint-Venant's principle or something. We have to represent each load by another equivalent direct load with a moment. So here we are taking only moment. Here, in addition to moment, we are getting another direct load. This is actually the equilibrium condition which we have to take up at each point. Instead of that, considering equilibrium at each point, straight away I am taking moment. So at this particular point, we have to be careful, this point. So that means, in addition to that moment 3, whatever we have here, that moment 3 due to this load, all along this beam point same. Even B also it will be 3. But in addition to that, same 3 will continue here. But in addition to that 3, this also will be active. So this point, you have to be very, very careful. Whenever we have, even here also, external load also, if it is given, that same thing you have to follow. Otherwise, if you take from sections one half of the frame from right side, another half from left side, this problem will not be there. Otherwise, only one side if you go, then this point you have to be careful. So, in addition to these 3, another, due to this 1 into x, you have to take. This is, because this is positive, this will be negative, mind it. Because this load, this gives 1 into x. It is creating hogging moment here, not sagging moment. This creates sagging, this creates hogging. This confusion will be there in your mind. Don't have that confusion. If you do mistake here, then the entire problem will go. So this you have to be very, very careful. Whatever the load we have, that load we have to bring it, transfer to this point with another equivalent same load in the same direction along with the moment. And that load, whatever we are taking, due to that load again, moment we have to take here. That is that. Okay. So this is M1. The moment that M1 is done, then again M2, we have to apply a unit load in the vertical direction and fill up this. This I will finish it first, then I will compute DL1, DL2, DL3 together. So if I apply unit load, again along same sections, I will calculate the moment. So this, on this portion B, C, it will not give any moment because it passes through that point. So naturally, M2 will be 0 for DC portion. Again, for this CE portion, this gives a moment, that is 1 into this distance x. X I am measuring from C. 1 into x, it is anti-clockwise here, clockwise here it is sagging type, so it is positive, so 1 into x, this due to vertical load. Then again at x3 it is 1 into this is x, so this distance also have to add, so it is 1 into x plus 2. This also have to be carefully do that, fill it up. Then when it comes here, so this same moment here, this particular thing I need not do. If I do that, equivalent opposite load here, this will not give any moment. It will create only axial force. This, it gives a moment that is this 1 into this distance, that is 6. Automatically it will come here. When I take moment about this, 1 into 6. And this, it passes through that, it will not create problem as it is here. This extra thing is not coming, only 1 into 6. It will come, again it is sagging type, it is 6. So here it is not 1 into 3. In addition to 1 into 3, this is coming. Whereas vertical load, it is along the column, only we need not have to.
Sir, in the BA member, when we're taking M value, capital M value, it's how it is minus 90 into X, sir?
Which
in
one?
BA, in BA member.
B?
BA.
BA member?
AB member, when we are computing M, capital M.
Capital M.
For this, 90 into 4, 360.
Yeah. This also, you just do the same thing.
Yes, sir. That is 20
Yeah.
into X, right, sir?
This 90, this 90.
90 into 4.
And that be origin.
Yes, sir.
Origin, you replace this by equivalent two loads, 90, 90 and B.
Yes, sir.
Origin. So, this 90 and this 90, it will create a moment.
Yes, sir.
That is 90 into distance is 4, 360. Whereas this 90, it goes. It goes to the foundation.
Yes,
it
sir.
is not creating moment. We are calculating only the moment. That's why I have taken only.
360, but it is 20 into X, right, sir?
Then this is 20 into x. Acha.
Yes, sir.
Not 20 into
Yes,
x.
yes, yes.
That is one.
Okay.
20 into x. That's a mistake which has
Yes,
been
sir.
done there. Yes, you are right.
Yes, sir.
That is not 90 x.
Yes,
It
sir,
is
that's right.
due to that load. I told my
Yes, sir. Yes,
colleague while writing
Yes, sir.
that mistake has been committed. It's
Yes, sir.
20. Okay, fine. Next, here on same lines, that particular thing will not come, it is only 6. This, if it is understood, well, there is nothing much here, it is only a question of integration and evaluating this, computing this F matrix, coming up with the result. Then next, another M3 computation, we had to apply unit, moment, along the direction, coordinate 3, so this is x1, this is x2 section, x3 section, x4 section, point B, point C, point E, point B, and point A. So here it is a moment, so the question of replacing the load or shifting that load by which you are taking the moment to the origin selected will not come into picture at all because it is a moment. Only if it is direct load, then only the question of replacing it by two equal direct loads you have to do and calculate it. Otherwise you need not have to bother. Here it is at section x1, it is 1, section x2, again 1, no question of lever arm, it is the moment itself. Section x3, again 1, section x4, again 1, and it is giving a sagging type of moment. It is acting like this, here also acting like this, so it is sagging type. Tension is inside. So naturally when it is tension is inside, it is sagging.
In this column, sir, in AB also similar effect.
I mean, AB also like that only, you know. AB section this, so it is like this. Here also it is like this. Tension. If you take this section x2, applied moment is this way. Resisting will be this way. So it is sagging. Sagging inside. Sagging type only. So inside tension. So it is positive. So in very way it is 1, 1, 1. So after having prepared the table, so you use this formula straight away, work out DL1, DL2, DL3 and that's all. And of course F we can compute afterwards. For that also I will give you. So DL1 is equal to 1 over 2EI, I will take it outside. For the quotient MM1, M into M1. For quotient DC, it is 0. This is also 0. I need not have to bother. Only this. MM1 is 90 into 3, 270x. So it is minus 270x integral between 0 to 4. These two are 0, only this portion EB is coming to picture into dx. Then plus, because it is summation for all that segments. Here it is 20x minus 360 into 3 minus x, that is varied between 0 to 6. So it is, my first I will take this, minus 20x into minus x, it is plus 20x squared. Then minus 20x into 3, minus 60x, minus this is plus 360x, plus 360 minus 60, it is 300. Correct, huh?
Yes, sir. Plus 300.
300
Plus 300x.
plus 300. 300x plus 360x minus 60 is plus 300. Then this 360 into 3 minus
1080.
1080. This is into dx. That's all. So I have covered that entire section, all the 4 sections. These two are 0, 0. MM1 for this, I have multiplied this. Now I have to integrate it. It is just integration. So 1 over 2EA already I have taken outside because EI is there, that I have taken outside all constants. 2EI into, this is x squared by 2, integral of x dx. X squared by 2 means it is 4 squared by 2, that is 16 by 2, 18. 18 into 270.
4,860.
4,860.
860.
Okay. Next here, plus it is integral x squared dx x cube by 3. X cube means it is 6 cube, 216 divided by 3, that is 72. 72 into 20, that is 1440. That's the value here. Next, coming to here, it is x squared by 2. X squared by 2 means 36 by 2, 18. 18 into 300, 5400. Then here, it is x, x is 6. 6 into 1080.
6480.
6480. So this you can simplify, find out. Well, minus 4860 plus 1440 plus 5400 minus 6480 divided by 2.
Minus 2250.
Minus,
2250.
is it right? Any mistake? We come to this 300, is it okay?
300.
Just check once.
150 into 6.
Because this is
Sir,
minus
that is
20.
900, sir.
Huh?
That is 900. 300 into x square by 2.
Sorry, x squared by 2.
Yes, sir.
So that is 36 by 2, 18. That's okay.
36 by 2, 18 into 300. Yes, right, sir.
18 into 300, 5400, correct? No?
Yes, sir.
Is it all right?
Yes, sir.
This also 270 into 16 by 2. That is 8 into 270. This is 16 by 8. 8 into 270.
Minus 2160.
minus
60.
2160. Now you just see.
Minus 1548.
Minus
1548.
1548.
48.
And at least once you check all these values. Then dn2 equals, we have to take mm2. mm2, here this into this 0, this into this also 0, only this. So as usual, 1 over 2ei into this 90x into x plus 2. That is minus 90x square minus 180x. This integral between 0 to 4. Minus 90x into x plus 2. That is minus 90x square minus 180x into dx. Next, 0 to 6. This minus 20x minus 360 into 6. That is equal to, you take first this, 6 into minus 20, that is minus 120x. And minus 360 into 6, that is minus
2160.
2160 into dx. This you have to integrate, you will get dl2. This is equal to 1 over 2ei into, this is integral x square dx, x cubed by 3, that is 64 by 3, that is 64 into 30, 1920.
1920.
This is integral x dx, x squared by 2, that is 16 by 2, 8 into minus 180, 40, 40. Then this integral x squared by 2, 36 by 2, 18 into 120, 2160. Then this is minus 2160 into 6, 12960. So this, you can simplify, all are negative, you can add it, 12,960 plus 2,160 plus 1440 plus 1920 divided by 2. That
Minus 9,000.
minus 9,240.
240.
Perfectly all right. Divided by 9. Next, DL3. Now, DL3 equals, on similar lines, I will take 1 over 2ei outside, 2ei into this mm3. Correct?
Yes, sir.
It is mm3. It is 0, 0. It is just
Minus
90x.
90x.
Integral 0 to 4 minus 90x dx, then plus this minus 20x into minus 360. That's integral 0 to 6 minus 20x minus 360 dx. That's all. So this is 1 over 2ei. This is integral x dx, x squared by 2, that is 16 by 2, 8 into minus 19, that is minus 720. Then this x squared by 2, that is 36 by 2, 18 into 20, that is 360. Here it is 360 into x is 6, so it is minus 6, 2160. This you can find out. 2160 plus 360 plus 720 divided by 2.
Minus 1620.
Minus
1620.
1620 divided by
Yeah.
ei. Therefore, I have generated this D matrix. D matrix is nothing but minus DL1. So all that are minus, so I can take that minus or minus plus 1 over di and take it outside. The first one, of course, this you checked once, it has to be 900, not that. Anyway, I will take that. This only I have doubt if I remember to have worked out that. Others are okay. This is 9240 and this is 1620. It is plus only because it is minus DL1 minus DL2. So this is our D matrix. Second step over. Then third step to find flexibility matrix, because for calculating all D and F inverse I have to find out. This already I computed. So I have to compute only F. If I compute F, it's all done. So I compute F. So for that F computation, it is again we can use the same table. You can remember this formula for finding out coefficients of flexibility matrix. F II coefficient, it is given by sigma of integral m I square dx. Then Fij is coefficient Fij is given by sigma of mi, that is integral of mi mj dx divided by n. You can remember this for finding the flexibility coefficient. As I have given the formula for dl computations, so these are also displacement only. This same unit load, again one more unit load, it becomes mi at the same coordinate. At other coordinate also, if it is there, mij, you have to multiply that. So first you will take, since there are 3 coordinates, your flexibility matrix size, F, it is 3 by 3, that is F11, F12, F13, F21, F22, F23, then F31, F32, F33. So it's a big 3 by 3 matrix you have to generate. So all these coefficients, I have given the formula, you use that straight away and table we generated. I will take first F11, that is Fii. I is 1. That means sigma m1 square I have to take. M1 square I have. So say F11 is 1 over 2di into, because there are, this first one is 0, this it is there. Okay, 1 over 2ei will take it outside. So it is ei 2. So I will multiply by 2. Integral 0 to 3 of this x square dx, first one, m1 square dx. Then plus this 2 I have taken because 1 over 2ei I have taken outside. Then here it is 1 over 2ei only, it is 9. 0 to 9 dx, then plus 0 to 4 9 dx, then plus 0 to 6, it is 3 minus x whole square, that is x square minus 6x plus 9 dx. That is your F11. I will evaluate this integral 1 over 2ei. This is x cubed by 3, that is 3 cubed by 3, it is 9. 9 into 2, 18. This is 9 integral dx, x is 2, 2 into 9, again 18. Then here, the 9 into 4, 36. Here, it is x cubed by 3, 6 cubed by 3, 216, divided by 3, 72. Then here, minus x squared by 2, that is 36 by 2, 18, 18 into 6, 108, then 9 into 6, 54. So this is the integration values. We can simplify this. 36, 36, 72, 72, 72. That is
Total 90.
144.
90 by 2, 45.
Huh?
45.
45. That by 2 you have taken. So it is 45 by
EI.
EI. Good. Next, I will find out F22. All diagonal elements first I will determine, then the others. F22 is equal to 1 over this. F22 means this square.
M22 square. M2
1
square.
over
2EI.
2EI integral 0 to 2. This is 0, this is x square dx plus 0 to 4. It is x plus 2 square. That is x square plus 4x plus 4 dx, and then last is 0 to 6. This square, that is 36. That is 23. This is F22. Again integrate 1 over 2EI. This is x cubed by 3, that is 2 cubed by 3, 8 by 3. This x cubed by 3, which is 4 cubed by 3, that is 4 cubed means 64 by 3. Here it is x squared by 2, that is 16 by 2, 8. 8 into 4, 32. Then this 4 into x, 4 into 4, 16. This is 36 into 6, 216. So this is that. So this 64 plus 8, 72 by 3, it is 24. 24 plus 32, 56. 56 plus 16, 72, 74, 80,
So totally 144 divided by EI.
144.
By EI.
By after
Yes.
dividing by 2, 5, 144 divided by
EI.
EI. That is F22. Then you can compute F33, F33 on similar lines, 1 over 2 EI, all are 1 square dx. So it is
2 is
0 to, this of
2
course 2 I have to take because
Previously
it
0.
is EI value only, 0 to 3 of 1 dx plus 0 to 4, 1 dx,
So 0 to 2.
2, 0 to 4, 1 dx, 0 to 6, 1 dx. So this is 1 over 2 EI, this is x means 3,
6.
3 into 2, 6, this is
2.
2,
4.
this is 4,
6.
plus 4, this is plus 6, this is 6 plus 4,
18
10,
by 2,
10, 18, 18 by 2,
9
it
by
is
8.
9 divided by EI, that is your F33. Then F12 equals F21, that is nothing but M1, M2. M1, M2 means I have to take this. First one is 0, again 1 over 2 EI, I will take it outside. First one is 0, this is 3 into
X.
x. Integral 0 to 2 of 3x dx plus integral 0 to 4 of M1,
3x plus
M2.
6.
It is 3x plus 6. 3x plus 6 dx. Then 0 to 6 of 6 into 3 minus x, that is minus 6x plus 18 dx. That's all. So this is my F12, F21. So in this, if you simplify 1 over 2 EI, integral x dx x squared by 2, that is 2 squared by 2, that is 2 into 3,
6.
6. Then this is again
X squared
16
by
by 2,
8,
8
24.
into 3, 24.
6 into 8. 24.
Then 6 into 4,
24.
24. Then this is x squared by 2, 36 by 2, 18. 18 into 6, that is minus 108. This is 18 into x,
6.
18 into 6, that is 108. This and this will cancel. You have 48 plus 6, 54 by 2, 27 divided by the that is my F1 to F2 1 and that. That will work out F1, 2, 3. I will take out F2, 3 that is equal to F3, 2 because always it is symmetric. I am working this now 2, 3, 3, 2. So that is nothing but again I will take 1 over 2 outside 2, 3. I have to multiply this. It is 0. Next,
Yes.
it is 0 to 2. Integral 0 to 2, that is x dx, and 0 to 4, x plus 2 into 1. That is x plus 2 dx plus 0 to 6 of 6 into 1, 6 dx. This I have to integrate. So this is nothing but 1 over vi. This is x squared by 2, that is 2. This is again x squared by 2, that is 16 by 2, 8. This is 2 into x, 2 into 4, 8. This is 6 into 6, 36.
54 by
2. This is also 27 by EI only.
27 by
27 by
EI.
Then last thing, F1 3, F3 1. Because I have taken maximum indeterminacy 3 by 3 as per your syllabus. Maximum indeterminacy on unequal leg, all things it has come into picture. Naturally it is little bit lengthy, it doesn't matter. So it is 1 over 2 EI 1 3. I have to multiply this. It is
Yes.
x 0 to again 2 into 0 to 3 of x. First one.
Yes, sir.
X dx plus 0 to 2 of that is 3 into 1, 3. Then plus 0 to 4 of
3.
3 into 1, 3. Then 0 to 6 of it is 3 minus
3
x.
minus x.
That is minus x plus 3 dx. This you have to evaluate. So this is nothing but 1 over 2 EI. This is x squared by 2, 9 by 2.
4.5 into 9.
We have 9. This is 6. This is 12. This is minus 6. Not
6 square
6 squared by 2, 18. 36 by 2.
Plus 18.
And this is 3 into 6, 18.
Plus 18.
So this and this cancels. 18 plus 9, 27 by 2. It is 13.5 by
EI.
yeah. So I have generated the full flexibility matrix. F, like 3 by 3. F is equal to 1 over
EI.
EI is
F1
into
45.
F1 1 is 45. Then F1 2, F2 1, that is
27.
7. Or I will take 9 outside. If I take 9 outside, this will be 5. This is 3. Okay. Then F1331, that is 9 is 1.5. So 3, 1.5. Then F22, I got 144. That means 15. 16. 144 by 9, that is 16. Then this F23, it is 27. So 9 I have taken outside, it is 3. And F33 is
1.
That is 3, 3.
9 by 1.
It is 1. So this is my F matrix. So I will find out the determinant of this. This is nothing but 5 into, why I have written in determinant means I can find inverse. So by finding that inverse 1 over delta into adjoint of this matrix. That is 5 into 16 minus 9. 16 minus 9 means 7.
7.
Next, plus 3 into, oh, this is minus. Minus, I will take it inside. So this is 3 minus 4.5, that's minus 1.5. Minus of minus, it will be plus 1.5. Then this
Plus
1.5 into
9 by
9 minus 24. 24 minus 9 means it is minus 15. 9 minus 16 into 1.5 is 24.
Minus 15.
9 minus
15.
So this is nothing but 35 plus 4.5. This is 22.5. This you can simplify. 39.5 minus 22.5. That is
17.
17. Okay. Therefore, F inverse. Because I have to calculate F inverse. After calculating F inverse, there is nothing more to it, it is multiplication for finding R. So therefore, F inverse is nothing but 1 over determinant
1 by
that is
17.
9 by EI. If I take
EI by 9.
inverse, it is EI by 9. That 9 into 17. 153 into. So this, for this cofactor is 16 minus 3, that is 7. I have already determined here, that's why I wrote these figures. Then second one, 1.5. Then third one, minus 15. This first row column, it is over. Next, I have to take this middle one. 5 minus 2.25. I take 2.7.
2.75.
Huh?
Yes, sir. 2.75.
75. Then this, it is 15 minus 4.5. 10.5
Yes, sir.
minus 10.5. This is minus 10.5. Lastly, this 80 minus 9, 71.
71.
Okay. So this is
F
F
inverse.
inverse. Therefore, R equals, R is my HD, BD, MD is equal to this. D is 1 over DI 900, 9240, 1620 multiplied by 1 over 153 into this. This is inverse of matrix. 7, 1.5 minus 15, 1.5 minus 15, 2.75 minus 10.5 minus 10.5, 71. EI, how this is? I didn't write EI, I didn't write here. EI will go.
Yes, sir.
So that EI and this EI get cancelled. You have got this HD, BD, MD value. This is nothing but, because this is 3 by 1 matrix, this is this is 3 by,
3.
oh, this I have to take the other side.
Yes, sir.
Okay, anyway, this side write it. This is, in that formula, it is F inverse D. That is 1 over DI 900, 9240, 1620. This answer. So This is 3 by 3, this is 3 by 1, so resulting will be a 3 by 1. Right away. That will be. So this you can find out. 7 into 900.
So that is minus 27.
1.5 into 9240 minus 15
Yes, sir.
1520
Divided by
divide
153.
153.
Minus 27.
Minus
27.
27.
7.
27. You can compare this now with your earlier results. Of course, earlier you have not find out HD, only MD you can
Yes,
compute
sir.
and compare. 1.5 into 900 plus 2.75 into 9240 minus 10.5 into 1620, that divided by 153.
63.7.
Huh?
63.7.
Fine. 63.7.
7.
And lastly this value you can compare. MD, which you have already got. That is minus 15 to 900 minus 10.5 into 9240 plus 71 into 1620.
Divided by 153.
Huh?
29.41.
Fine.
29.4.
Okay. So this is kilonewton meter, this is kilonewton, because MD is in kilonewton meter. This you can
So
compare.
that is 29.4, sir.
20,
9.4.
fine. 29.
Ah, sir.
Anyway, just check once.
Yes, sir.
So now you got this frame. So with this loading 90, 20, and so this 27 is minus. I have to take direction like this. Earlier I have taken the other way. This is 27 and this is 63.7 and this is like this itself 29.4. Here this is 27, this is 20. Here this also should be 7. Because
Yes, sir.
now sum of all horizontal
equilibrium.
forces should be 0. Reaction I am determining here. So here it
90
is
minus
90 down,
63.7.
63.7 up. Therefore here it should be
54 points.
26.3. Correct? Huh?
Yes, sir.
Okay. This is that. Kilonewton, 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 kilonewton meter. Now you can take moment about T of all the forces. You can find this MA. So that is MA equals all this and sum it up and find out that MB. So if I take sigma MB equals 0, I will get MA. MA I will take to start with this direction. So that is MA, then this 7 into 3, that is in the opposite direction, minus 7 into 3. This is 3, because this is 6 meters, this is 3 meters, so this is 3 meters. 7 into 3, then MA I have taken, then this 26.3, 26.3 into 6, so that is again in the same direction, minus,
Sir,
it is
MA.
plus, it is plus, then this 20, 20 into 3, that is clockwise, plus 20 into 3, then this 90 into 2, 180 anti-clockwise. Anti-clockwise it is minus 90 into 2. That's all. Moment due to this, moment due to this, moment due to this. This I have taken as the unknown and this. All these three will not give any moment, that is equal to
16 point.
So we can find out MJ
16.8.
Huh?
16.8.
16.
Yes, sir.
Check once. I think 12 point something I got, I remember. 16. 21 plus 130.
Sir, minus 21.
Minus
Minus 21. plus
137.8
137.8
plus 60,
plus 60
okay,
minus 180
minus 180. You got?
minus 3.2.
Oh.
So 26.
Then this I have omitted.
Yes, sir.
That I have to take. You didn't observe that. This is minus.
Yes, sir.
Minus 29.4, because that moment I have to take. These two will not give any moment, but
Yes,
this
sir.
will give.
Other side, couple.
Now,
Point
this MA,
3 into 6 plus 60 minus 180 minus 29.4 minus 12.6.
yes, this is what I remember. 12.6. That is minus. Minus means now I have taken it as positive.
Yes,
Because it is stacking inside like that I have
So
taken.
that is,
I am getting minus.
so that value, if you take right side, will become 12.6.
Which one?
The total minus 21 plus 137. The total is
That is
minus.
you take that
That
side.
side will become plus.
That is how we have to give, because this is equal to 0. I have
0.
taken.
Yes, sir.
MA only have calculated.
Yes, sir.
So that is this direction. Whatever
12.6.
it is. Okay. Now when once you know that, right? So you can plot separately. You can find moment on same lines. MB, MC also you can find out the support moments on same line. Taking moment about either B or C, you can plot the
Bending
bending moment diagram. As well as shear force also in the individually each member. Shear force is, it will be constant at the ends, so you can plot it. So with this, the most tough problem also we have that maximum indeterminacy allowed in your syllabus, 3 degree of static indeterminacy. And all that I have worked out by hand computation, even this inversion, integration, everything by hand computation. You can do with calculator as usual, programmable calculator, you can use it. So another 15 minutes, cushion you can keep it. So there won't be any problem.
Thank you, sir.
With that,